Once again, welcome to the physics video lecture. This is Physics 4B, video lecture 17. So we're talking about circuits now, currents, Ohm's law, things like that. I think we ended with the internal resistance of the battery, and I'll put a homework assignment of a couple of these things up at the end of the hour. So let's see, we have, I'll just draw a circuit. And V or delta V, I use them interchangeably, but the long and the short lines here indicate the positive and negative poles of the battery. We get a current going from plus to minus, and there's our resistance. And we have Ohm's law. V equals R times I. Good. I also had, let's just view this as the first part here. Second part was to take to account for the fact that no battery can deliver an infinite current, okay? And here we could just have a sufficiently small, for a given voltage, a sufficiently small resistance, and the current could grow without bounds. So in reality, we said we actually have a battery, and we label this E here, and it has an internal resistance. And so if we have these points A and B, we can even draw this in. You know, there's a battery, right? There we go. And we hook this up to the same circuit, and now we're not going to have infinite anything, because this resistance is always in play. So this was the internal resistance. Now we're going to leave it off typically, now that we know that it's there in the concrete case. So typically when we set up circuits, we'll just have a voltage, but we have to be aware of that. So that was the internal resistance of the battery. Cannot be eliminated. Okay, so what we're going to do next is some combinations of resistors, slightly more complicated circuits. And so resistors in series, just the way we had with the capacitors, we're going to put them in series and we'll put them in parallel. So in series and parallel. We'll start with the series circuit. So we have, go ahead and have R sub 1, and then another resistor with R sub 2, and then we'll complete our circuit here. And now, we actually did this the other day, but let's be explicit about it. So now if we have a current flowing through here, conservation of charge is telling us that the current is the same throughout the entire circuit, okay? Therefore, if we're going through the resistor number 1, it's a 1 there, we have V1 is equal to I R1, and then the same for the resistor number 2, V2 is equal to I R2. But these voltage drops have to be equal to the battery voltage drop. So we have V, and I'll put here in words, same current through each resistor. Okay. So for that reason, V is V1 plus V2. IR1 plus IR2. So IR1 plus R2. And if we equate this right here, we see that the equivalent resistance is R1 plus R2. So R equivalent, or series, is just R1 plus R2 plus R3 plus and so on. As many as you have. They just add linearly. And that is consistent with the idea that if we had a length of wire, the resistance was proportional to the linear length. Okay. So that's no surprise. What about parallel? Parallel is interesting. So this was series for our parallel resistors. Let's go ahead and put the battery down here. And it's enough for us to just do 2. So here we have R1 and R2. The principle now is not that the current is the same through each resistor, but that the potential drop is the same across each resistor. And in fact, it is just this potential drop right here, this V. So what we have, we can use this part of the board, is we're just going to use Ohm's law again, but now we have I sub 1 is equal to V divided by R sub 1. I sub 2 is equal to V divided by R sub 2. Okay. And if we had a whole ladder of these, if we had several more, it would always be the same thing. And V is equal to I total. Okay. So you have I sub right here, but then across this one you have I sub 1, across this one you have I sub 2. So V is equal to I total R equivalent. And you can see what's going to happen here. V is equal to V over R1 plus V over R2. V times 1 over R1 plus 1 over R2. Actually, hold on. Oh, times R equivalent. Okay. So this is an identity, and we're going to have from this equaling 1, R equivalent times this sum equaling 1, we immediately get 1 over R equivalent is equal to 1 over R1 plus 1 over R2, and we could extend that as well. So it's the sum of the reciprocals. Now it looks like we've seen these two laws with our capacitors, but you have to be careful, they've been reversed. In other words, that pattern, the linear addition, that was, in the capacitors, that was the parallel, okay? So let's go ahead and summarize this. Let's summarize these. So we have, for resistors in series and parallel, we have series R equivalent is equal to R1 plus R2 plus and so on. And parallel 1 over R equivalent 1 over R1 plus 1 over R2 plus and so on. Now I'm just going to warn you, it's very common to make a mistake. And the very common student mistake is to say R equivalent is equal to 1 over R1 plus 1 over R2. Okay, it's 1 over R equivalent, and so you have to do a couple of steps if you put this in a circuit. So I'll just put this as a warning, note, avoid, I've seen this done often enough, avoid writing or calculating with R equivalent equals 1 over R1 plus 1 over R2. This is wrong. So yeah, but yeah, the same formulas we had with the capacitances, except the cases are reversed. And you can use these to do more complicated circuits. Go ahead and leave that up. Erase this. So you can then do some combinations of resistors. So combinations would look something like, you've got, maybe you split them up like this. Okay, and then you could do another one of these. Bring it into here. Okay. And should we name these things? We'd have R1, R2, R3, R4, and R5. So you have some more complicated combination. You could say if we knew these equivalent capacitances, we could just put them all in 3 in series. So we do it step by step. We can say R equivalent is equal to R sub 1, 2, I don't know what it is yet, okay, plus R sub 3 plus R sub 4, 5. That's my first step. And then I have to say 1 over R sub 1, 2 is equal to 1 over R1 plus 1 over R2. And I have to calculate this, and then I have to invert it. Okay. And that gives me that number, R sub 1, 2, and I do the same thing for R sub 4, 5. So you have combinations possible as well. And once you have these combinations, once you have this whole thing analyzed, you can continue on and use Ohm's law to get the total current. And once you have the total current, then you can get the voltage drops across each of these, and get the voltage drops across each of them. You know, you get the current through each individual, and you can eventually say, find all the voltage drops, all the powers being dissipated, and all of the currents. So that would be the complete analysis of one of these. And we'll do a couple of these on the homework, and then that's good. Then we understand that. So those are the combinations. Now, if the combinations get more complicated, there are a couple of rules that just go back to the fundamentals. So if you have a more complicated system, you can invoke conservation of charge and conservation of energy in a way that was discovered by Kirchhoffs, is referred to as Kirchhoffs rules. We go ahead and send those, or send this up, have a look at those. So for more complicated circuits, so next we will talk about the Kirchhoff rules. Kirchhoff's rules. And it's not necessarily just complicated circuits, but as soon as we set up our differential equation or time-dependent circuits, we'll make good use of these. So Kirchhoff's rules are as follows. We have the junctions. So say we have a junction here, and we'll say there's I sub 1, I sub 2, I sub 3. The rule is that the sum of all the currents going into a junction equals the sum of all the currents leaving the junction. And that is just conservation of charge, right? This I sub 1 has to split up into 2 and 3. So, sum of currents entering, how do I have that formulated here? Yeah. Entering a junction equals the sum of the currents leaving. And you draw your directions, and then you've got your sum equals sum. On the other hand, I could reverse the direction of one of these. Like I could have I sub 3 pointing the other way, and then it would have been I sub 1 plus I sub 3 is equal to I sub 2. Okay. But that's conservation of charge. So, conservation of charge. And then so that's the first rule. The second rule is the loop rule. And that says that the sum of all voltage drops around a loop equals 0. Let me draw a slightly less trivial version of what we've been talking about. Say we got V sub 1, we've got R. Let's put a second battery here, V sub 2. So the loop rule says the sum of all the potential drops is equal to 0. Sum of, I'm going to formulate that, potential changes equals 0. Just put it in words. Potential changes around a closed loop. Closed loop is equal to 0. So the example we have right here, we're going to choose our arrows here clockwise for our current, and we'll start right here, and we'll end right here. So crossing this battery, go from negative to positive, so we have V sub 1 positive, then minus IR when we go across the resistor. Now when we cross this battery here, we're going from higher to lower potential, so we have minus V2, and then we made it back to the beginning here. So I drew the arrow, right, with I here, and I'm taking the magnitudes of these potentials here, delta V. So the question is, what happens if V2 is greater than V1? Then in reality, the direction of the current is going to be reversed. But that'll come out in the algebra as well. So if you just go ahead and set this up, formulate it, and do your calculation, and if the current comes out negative, that just means you change the direction of your arrow. Okay, so nothing can go wrong. That's the idea here. So we've got the junction rule and the loop rule. We don't need them for these simple circuits. Although with the opposing batteries is actually pretty good. For example, if the batteries are opposing here, and if they had the equal voltage on each one, then no current would flow at all. Right, we'd have V1 minus V2 equals 0, current would be 0. So where these formulas become more necessary is when you have a complicated circuit where you can't just invoke Ohm's law trivially. Then you write out as many loops and junction rules as you have, and that generally gives you enough equations to solve for your unknowns. Just to show what we would have here, a simple example. So let's just go ahead and have one battery. Now we know we can do this with an equivalent resistance, of course. But actually, how about we put a battery right here? Okay. Now it's no longer a trivial problem. Okay. So there's V1, there's V2, and we want all of our currents. So we're just going to say we've got I sub 1, I sub 2, and we'll just draw it in this direction. And of course, this current here corresponds to that current there. So here, it's actually enough. So now, let's go ahead and do our junction rule up here. I sub 1, I'm going to have to, here's what we'll do. We'll just call this I, and then we'll call this one I sub 1, and this one I sub 2. So I sub 1 is going through R sub 1, I sub 2 is going through R sub 2. And this is a current where I equals I sub 1 plus I sub 2. Then we have two loops here. So the leftmost loop here, we'll start here, V1, and then minus, we don't know anything about I here, but we have minus I1 or 1 equals 0. Okay, so that was this loop right here. And now we'll do the outside loop. So we will have V1 again, although there's actually another way to do it, but let's go ahead and do it this way. So we'll have V1 again, and then we have a voltage drop here, so minus I2 R2. And then since we're crossing V2 from, better make up my mind here. Okay, we're crossing from the shorter to the longer, so that is plus V2 is equal to 0. So that way we've set up Kirchhoff's rules. It would be possible to instead of writing this one here, to do just the loop on the right-hand loop right there, be equivalent. Okay, good. So then you can solve your three equations for three unknowns. Three equations, three unknowns. Good. Let's see how we're doing time-wise. Okay, perfect. So three equations, three unknowns. Okay, so I want to get to the time-dependent circuits next. Oh, actually, for Kirchhoff, I see I have some conventions here. These are important. I've used them implicitly, but let's make sure we write them down. So for formulating Kirchhoff's rules, the first thing you do, you draw in the current direction. So you have a circuit, you draw the currents in. It doesn't matter if they're the correct directions or not, because the algebra is going to give you, it'll reverse it for you. So you draw in the currents, and then since you have those directions, if you have A to B and R here, if you're crossing the loop in this direction, then you have negative IR, okay, for your voltage drop. Okay. But if you were to be, if your current direction was here, and you go across, and you do your loop in the opposite direction, then you have to give a plus IR. Okay. That's important. Yeah, and what we did here, trivially, we could just reverse the directions of our loops and we'd get minus signs everywhere we have plus signs, okay? And vice versa. So that would work. And good enough. Good, so you've got Kirchhoff's rules, and you can choose. So if you have a problem with resistors, you think you can nail it without Kirchhoff's rules, fine. If it's easier just to set them up, and once it gets, this one of course was trivial either way. But once it gets a little more difficult, then you can use Kirchhoff's rules. I want to do a time-dependent circuit now, which is where they actually get more interesting. And we'll use Kirchhoff's rules for that as well. So our next topic is charging and discharging a capacitor. So we had the formula for the capacitor. But the charging of a capacitor and the discharging takes place over time, and we had just something that did not involve the time. Charging, I'll just start with charging a capacitor. So here's what we had. We had Q equals CV or C delta V. And our picture here was, here's our battery, and here's our capacitor. Okay. Capacitor with capacitance C, and then we said, well, there's going to be some positive charge on this side and some negative charge on that side. But if we think of this, hooking up this battery with an empty capacitor and then closing a switch, it's actually going to take some time for this to happen. So that's what we talk about when we're saying we're going to charge the capacitor. So here there was no time dependence. Now we're going to, let's draw it this way. Yeah. So like the number thing. So here's one. Now consider a battery, a capacitor, and a resistor. So there's a resistor, here's a capacitor, and here is a switch. So as soon as we close the switch, a current's going to flow. We're going to go ahead and label this not V, but E, but yes, that's the voltage. RC. So this is called an RC circuit. And we're going to close the switch. And current flows. Right, so we close the switch. Current flows here. And what's happening is we're going to build up some positive charge here and correspondingly build up some negative charge here. So the current flowing clockwise in this case. So we're going to use Kirchhoff's loop rule, and we have, starting here at the left corner, E minus IR. What about here? Okay. Well, here we have Q divided by C. Okay. So minus Q divided by C. Because remember, we're going from plus to minus, here to lower, so we have minus Q over C is equal to 0. And this Q is something that's changing in time. Now, we have Q and we have I, but this is going to be a differential equation because I is equal to dQ over dt. So we have a first order differential equation that I'm going to show you guys how to solve. And we'll get the time we'll get the time behavior, but since we started with this idea of it being fully charged, what's going to have to happen is that as time gets larger, this thing ends up fully charged. Okay, so it starts out with no charge on it, it ends up fully charged, at which point the charge will just be equal to C times this E here, which is our voltage. Let's have a look. So we'll put the current in there, get our differential equation, and then solve it and see what happens. So we have E minus R dQ dt minus Q over C is equal to 0. And what we have to do is solve for dQ on one side of the equation and dt on the other. So that's called separation of variables. Yeah, so we'll do that in 2 steps. So we'll do the dQ dt first. dQ dt is equal to E minus Q over C, and we'll divide by R. Or dQ dt. Remember, that's the current, so just from Ohm's law, that's what we would have. Minus Q over RC. Okay. So the next thing we're going to do is do what's called separation of variables. Next, separation of variables. We're going to have the dQ and the dt separated. So we'll have dQ over E over R minus Q over RC is equal to the dt. Q over RC E over R. Okay. And I'm going to multiply both sides by 1 over RC. So I'll do it right here. RC, R times C. Okay. So I can do that. We're going to cancel there. That's going to cancel. And I have dQ over Q minus B times C is equal to minus dt over RC. Okay, so now I have it in a form where it's easy to integrate up, and that's what I'm going to do next. So now that I've just treated all our differentials algebraically the way we do, and we're going to integrate both sides. So this is a technique you can use on first order differential equations pretty confidently. So next, let's just write here, next integrate both sides. And what we're doing is dq dc here. We're going to go from 0 to q, so we have to call the q's and give it a little prime, those are integration variables. And on the right side, we'll have 1 over RC, and then integral dt, and a minus sign dt, from 0 to t, so also a t prime. And this is recognizably just a natural logarithm. So we have natural log of the upper bound minus the lower bound, so q minus ec over minus ec. Integrated both sides, right? Natural log. And on the right side, we just have minus t divided by r times c. So now we exponentiate both sides. So that just means we take the e to the left side and e to the right side. E to the natural log gives us the argument, so we have q minus ec over negative ec equals e to the minus t divided by rc. And then we solve for q. Solve for q, which is now a function of time. And what do we have there? Q is equal to E times C times 1 minus, okay, let's give the minus over there. And this brings over the plus sign to 1. 1 minus E minus T divided by RC. So there's our result. We're going to see it does everything we knew it would, or we hoped it would. So that's a function of time. So this is the charge, picture's gone. This is how the charge accumulates on the capacitor after you throw the switch. You throw the switch at t equals 0. At t equals 0, 1 minus 1, no charge. Okay. Now, as t goes to infinity, or t gets large, this exponential completely drops away. And then Q is E times C. Remember, this E is our voltage, so this is just the formula for the total charge of a charged capacitor. So let's graph this. T, Q, charging a capacitor. The RC circuit. Starts at 0, asymptotically up to here. We'll do a dotted line. Goes up like that. Okay. Now there's a really important point. What sets the time scale is this RC right here. So RC is a time constant. So when t is equal to tau, when t equals tau equals r times c, then what do we have? 1 minus 1 over e. Okay, so roughly 1 minus 1/3. So then we're roughly here, and then twice the time constant, 3 times the time constant. It's essentially, after that, it's very quickly saturated. So time constants are really important here, and it's the product of the resistance and the capacitance. Now, a good exercise is to convince yourself that this really is a time, that it has the units of seconds. So I leave that for you guys to do. Right? Unless we've made an egregious error, it has to be the case, right? We're just doing algebra here. But one thing we can do is just go to, actually here, units of RC equal, right? Knowing that they have to be time, here's one thing we can do. We can say V equals RI and Q equals CV, and then the R can be expressed as V over I, and the C can be expressed as Q over V. They cancel, and what are the units of Q over I? That's coulombs divided by coulombs per second, so that really is seconds, okay? Coulombs divided by coulombs per second is seconds. So yeah, the time constant, very important, really is 1. And so if you go back to our original circuit, you can see the speed with which the capacitor charges depends on this combination here. If the time constant is really small, well, if the resistance is small, the time constant is really small, okay? If the time constant is small, it means it charges up really rapidly. Consult the clock here. Okay, great. Good, so there's the charging of the capacitor, and next we'll do the discharging the charged capacitor. So we want to discharge the capacitor. And so, one, we can remove the battery. Then we have a charged capacitor. And then we complete the circuit. Then complete the circuit. There's a good little problem. There's a good problem on the homework that I think I'll assign to this as well. So yeah, then we're looking at the following. We still have a resistor. We have a capacitor. And a resistor. And this time the thing is charged. Let's say it had plus Q and minus Q. And then the formal current's going to go clockwise. And we will cross this thing, remember, Q equals, yeah, call it this way. You can see like that. So in terms of Kirchhoff's rule, we're going to cross this thing here. So we're looking at Q over C minus I times R is equal to 0. And again, we're going to have the I as the dq dt. And I is equal to dq dt. This time, though, I have to smuggle in a minus sign by hand. And that's because, so the minus sign is because the charge is decreasing, okay? So if the charge is decreasing, I have a negative derivative here. Negative times negative is positive, and that's the positive sign of the current. Okay, so sign because charge is decreasing. Okay, so having said that, let's set up our equation. Now, what do we have? We have, and I can use lowercase q for what it's worth. Yeah. Q over C is equal to negative R dq dt. Again, I put that minus sign in by hand because it's a derivative now and the quantity is decreasing. Eventually, the capacitor will be discharged, and all the energy in the capacitor, by the way, will have gone through the resistor and been radiated away somehow, okay? Dissipated. Good, so let's solve this differential equation. And we'll, first of all, we've got our dq dt is equal to minus q over rc. There's our time constant again. dq over q is equal to minus dt over rc. We're going to do the same thing with a slightly easier problem. Okay, so let's continue. And in fact, consult here. Good. So we've got both sides here. I actually should have kept that drawing up, but here it goes. So what we want to do is integrate and then draw a picture of our function. I may actually redraw the one I just erased. So what are our limits here? We have 0 t prime and q0 to q. And when we integrate the left side, we've got the natural log, and let's go ahead and prime. Integration, natural log q over q0 equal to minus t over rc, and now we exponentiate again, and to solve, we end up with q of t is equal to q0, which could have been our capital Q, but no problem, e to the minus t over rc. So we have charging it, and then we have discharging it. And what's the sketch of this thing look like? Let's go right underneath here. T, Q, at t equals 0, we just have either 0 is 1, so we have the Q0, and it just decays exponentially. And again, the time constant is very important. And here you see it's when Q is 1 over E, somewhere here. Because that really sets the time scale for the whole action. Okay. Mathematically, it takes till time goes to infinity for the thing to completely discharge or charge, but practically speaking, the exponential gets so small after a couple time constants that you're done in that sense. Good, so we had the charging and discharging. We had these really nice technique, separation of variables for first order differential equations. And yeah, the first time dependent behavior for these quantities. Consulting the clock once again. That's about where we're going to leave it. So I'm going to assign some homework problems and maybe say a word or two about each one. Yeah. This will be homework for the 17th lecture. So homework 17. Let's see here, chapter 25. Problems 69, 70, 73, 75, and what do I have here? 96. Better have a look at the book, see what that's all about. Okay. So we're now looking electric current and direct current circuits. Yeah, what do we have here? 69. Okay. Yeah, so 69 and 70 are very basic current potential drop problems. So these two are just currents and potential drops. Okay. So they don't really need much discussion. What about 73? 73 is a problem, internal resistance. So that's something I've done on the board basically. So you have a look at what I did on the board. And it's a question about a battery, with some numbers in there, but this we have on the board. And that would have been the previous lecture. 75. Yeah, 75 is a circuit with 5 resistors in total, and there you guys can just knock yourself out finding all the currents, the potential drops, and the dissipated power. Do they ask for the dissipated power? They don't even ask for the dissipated power. You're looking for all of the currents and the equivalent resistance. Okay, maybe we should add one. Power dissipated is also interesting. Do any of these ask for? Maybe I'll just ask you guys to do that. It's actually trivial. No big deal. Let's see. How about problem 96? 96 is a capacitor problem. Okay. So we've solved the charging of the capacitor, the discharging of the capacitor. You'll see they have a nice sketch that shows how you can have one circuit, one switch, you can charge it and discharge it. So it's actually a nice, this is a good one to study, okay? And then they just have some numerical questions about it. Oh, in fact, it's a good one. Energy stored in the capacitor as a function of time. Let me say a word about that. Let's get our circuit going. Yeah. So after you flip the switch with a fully loaded capacitor, you're left with this circuit diagram. Okay. And at time equals 0, all of the energy stored in there. Remember, we have the energy in terms of Q and C. So look up the energy there. The energy stored is going to be decreasing, and it's going to be dissipated in the resistor. Okay. So those two quantities, the energy dissipated over time should actually end up being the same as the original energy stored in the capacitor. In a circuit diagram like this, the energy dissipation all is taking place in the resistor. Okay? The capacitor is just ideal. So that's an interesting problem. You can tackle it from a couple of directions. Like you could take the total initial energy minus the energy dissipated, or you could use the capacitor formula. So that should be a good problem. And without further ado, I'll say see you guys next time.